We proceed in parameterization of surface in calculus. Parameterization of surface in calculus, that is something that is considered as the most advanced topic in calculus. Curl in calculus, flux in calculus. Now, the parameterization in calculus. Why it is considered as the most advanced thing? If we see the curl, if we see the curl, then it is line integral. If we see the flux, then it is surface integral. We have one more thing that is called directional derivative along a vector. But here, parameterization of a surface in calculus, where we will have derivative of a surface with respect to along another surface, and both may be in different coordinate system. So this is considered as the most advanced thing as far as calculus is concerned. Directional derivative of a surface in xy plane along surface in uv plane. Amazing, right? So this is what the discussion that we are pursuing. Okay, now consider that I have to calculate volume of a sphere. So sphere is centered at the origin. This is origin, and this is origin, and this is xy plane. Sphere is centered. So half of the sphere is above, half of the sphere is below. It is centered here. Fixed it at here. What is the volume of the sphere? The volume of the sphere is fxy dxy plane. Oops, I'm sorry. If I have, if I have, if I have x-axis and there is a curve like this, what is the area underneath this curve? What is the equation of your curve? That is fx, function over x. This is x-axis. Then fx dx. Now I have a surface above the xy plane. What is the equation of your surface is? fxy, function over x comma y, f small bracket x comma y bracket close, fxy. Then fxy dxy plane. Earlier fx dx. Here fxy dxy plane or dA. So simple, right? So what is the volume of a sphere? Then fxy dxy plane. What is the equation of your sphere? X square plus y square plus z square equal to a square. Then z equal to square root of a square minus x square minus y square. Z equal to square root of a square minus x square minus y square. Then fxy equal to square root of a square minus x square minus y square. Now if I fit into it, it becomes square root of a square minus x square minus y square dxy plane and integration over the region in xy plane. What is region in my xy plane? What do you mean by the region in xy plane? I'm talking about the way you calculate region in along x-axis, right? If this is the curve, if this is the curve, and if you're calculating the area underneath the curve, then this is the limit. This limit, where this curve is falling, lower limit, higher limit of the x-axis, that is the limit. Similarly, if this is the sphere and it is falling on the xy plane, wherever the intersection is, that is the region. There the limit is x left and xy. Here limit is the xy plane region, that is spherical. If the sphere is centered at the origin, half of the sphere is above, half the sphere is below, then the region on which the sphere surface is mapped on the xy plane is a circular. In circular region, square root of a square minus x square minus y square dxy plane. Please make it clear. What is dxy plane? Consider dx dy. Dx dy is the d area, because if I take area in xy plane, it will be dx dy. If I take a small dA area, it will be delta x delta y, delta x into delta y, dx dy. What is full now? Minus a to a, y, and x minus a to a, because it will form a circular region, then that is nothing but the radius of the sphere. Square root of a square minus x square minus y square dx dy. I cannot calculate it. It looks very difficult for me. Let's try with another coordinate system. X equal to r cos theta, y equal to r sin theta. There is another coordinate system called r theta plane. It is xy plane. Now I have fxy as dependent component. It dependent upon xy plane. Fxy, that is square root of a square minus x square minus y square. Now x square xy plane is no more independent. Xy plane is again dependent upon r theta plane. That is x equal to r cos theta, y equal to r sin theta. If that is the case, then how now I can replace it? Now the circular region, what we are talking about, that the circular region, what we are talking about in xy plane, that region would map to r theta plane, whatever the region it is. So if x equal to r cos theta, y equal to r sin theta, and x and y makes a circle, then what r theta would make, it is up to the function, whatever it is. Now the integration is again region on r theta plane. Earlier it was circular region on xy plane, it is region on r theta plane. Square root of a square minus x square minus y square. Square root of a square minus r square cos square theta minus r square sin square theta. Square root of a square minus r square. Dxy plane. Now dxy plane will go to dr theta. Dxy is dx dy. It cannot be directly dr d theta because x is r cos theta, y is r sin theta. So dx will be r minus sin theta d theta. Not true, because r is also variable, theta is also variable. If r is constant, then dx equal to r minus cos theta d theta, dy equal to r cos theta d theta, but both are variable. X equal to g r comma theta. X is a function over r and theta. X equal to g r theta. Y equal to g r theta. R and theta both are variable. If that is the case, then dx equal to, I don't know, what is then dxy plane. Now there are, this is called dA, d of area, dA or delta A. Delta A in xy plane is dx dy, delta x delta y. Delta delta r theta is dr d theta. But delta xy I cannot convert directly to the dr r theta plane. Then it will be dr d theta. Not true. What is d area dxy plane to dr theta plane conversion? Here the catch is how we go along, how d area will be converted into d area in r theta plane. There are three proofs for it. First proof is our proof, that we will discuss it first. Dxy plane, or I can say d in braces x comma y braces close, dxy plane. Dxy plane is nothing but dxy by dr theta into dr theta. D braces open small bracket, r comma theta bracket close, d and multiply by dr theta. Same thing as per the multiplication rule. Then dxy by dr theta is what? T into dr theta, that is dr d theta. Now it is converted to the region on r theta plane. It may not be circular region. I don't know what it is. And then square root of a square minus r square dx comma y by dr theta into dr d theta. Now what came as dx comma y by dr comma theta? It's not very difficult as per our principle. Now consider that I have xy plane and there is a surface on top of xy plane. This surface is z or function over x comma y. If there is a rectangle on xy plane, if there is a rectangle on xy plane, this rectangle would map on some area on the surface. It may not be rectangle here as per the fxy. Now on this rectangle there is a unit change. Then how much unit change I see on the area? This rectangle is mapped on an area here. If there is a unit change on xy plane rectangle, then how many unit change here I see on the area on the surface? Okay, d area on the surface by d xy plane. To calculate that, we take any point on the surface and call it p vector, position vector. That point coordinate is xi plus yj plus zk. From origin, if I draw the position vector xi plus yj plus zk, otherwise the point coordinate is x comma y comma j, xi plus yj plus zk. dp by dx, we have proved it. I believe three video back. dp by dx cross product dp by dy. If I do dp by dx cross product of dp by dy, this is nothing but we are trying to do d area on the surface by dxy plane. dp by dx cross dp by dy. Similarly, if I have r theta plane, there is a rectangle here. This rectangle is mapped into some area in xy plane, and there is a unit change along this rectangle, meter square. Rectangle area is meter square. If there is a unit change in area of this rectangle, how many unit change it would bring in this surface area? That is dxy by dr theta. Same thing, dxy by dr theta. Now denominator is r theta. Or if I have r theta plane, there is a rectangle here, and this rectangle is mapped to a surface that is xy, where x equal to gr theta and y equal to hr theta functions. Now what is dxy by dr theta? That is, if I take any p point here, position vector, then dp by dr cross dp by d theta, dr theta plane dp by dr cross dp by d theta, the way we did in the d surface area by dxy. Now dxy by dr theta, d dp by r cross dp by d theta. If that is the case, dp by dr cross dp by d theta is the real answer, then my original the volume calculation of the surface that we had taken, surface integration along a circle, region along a circle with radius a, that is x, y is minus a to a and x is minus a to a, the square root of a square minus x square minus y square dxy plane, now converted to surface region on r theta plane, square root of a square minus r square, and dxy converted into dxy by dr theta into dr theta. Dr theta, right, become dr d theta, and dxy by dr theta become dp by dp by dr cross dp by d theta. Now p is xi plus yj, so dxy by d theta in dxy by d theta I plus dy by d theta j cross with dxy by dr I plus dy by dxy by dri plus dxy by dy by dr. Okay, so dp by dr cross dp by dx. dp by dr is x, dxy by dri plus dy by drj cross product dxy by d theta I plus dy by d theta j. It will come as dx by d theta into dy by dr minus dx by dr into dy by d theta. So net integration is the region on r theta plane and the square root of a square minus r square into dx by dr into dy by dr minus dx by d theta, dx by dr into dy by d theta minus dx by d theta into dy by dr, and then dr d theta. This is the whole volume. Okay, this is one way of calculating dxy. Dxy, we did dxy by dr theta into dr theta. Now what, there are two more proof to it. Whatever is available in the book is, consider there is a rectangular region on r theta plane. Consider r theta plane, there is a rectangular region. Okay, this rectangular region is mapped into some surface area region on xy plane. Now divide this rectangular region into n by n rectangles, sub rectangle. there is a big rectangle on r theta plane divided into n by n sub-rectangles, where each rectangle is denoted as I comma j, where I is 0 to n minus 1 and j is 0 to n minus 1. Now I comma j is a sub-rectangle which has a width of delta r and delta theta, where x-axis is r and y-axis is theta. Delta r, delta theta. Lower bottom corner of that sub-rectangle is r comma theta. So there is a sub-rectangle whose lower bottom corner is r comma theta, width is delta r, height is delta theta. That is mapped into another sub-region. That sub-region is again divided into n, where each region is a parallelogram as per the book. Okay, so it is so infinitesimal small that I can consider it as a parallelogram. If that is the case, then parallelogram has a vector and another is b vector. B not be perpendicular somewhere. A vector and b vector. What is a vector? A vector has 2 points. One is r comma theta mapped to x comma y, and then right side r plus delta r comma theta mapped to x plus delta x comma y. Now the top side, there it is r comma theta plus delta theta, here mapped to x plus y plus delta y. So if that is the case, then this a vector, a vector is now this point minus this point. This point, the right hand point is g. G is a function over r and theta. So g r plus delta r comma theta I, g r plus delta r comma theta theta I plus h r plus delta r comma theta j, whereas the map the bottom left corner, that is r theta g r, so that is g r theta comma h r theta. If I talk about a vector, then it is g r plus delta r comma theta minus g r theta I, and plus h r plus delta r comma theta minus r minus h h, okay, plus h r plus delta r comma theta minus r minus h r comma theta j. Okay, this is the a vector. Similarly, there is a b vector, that is g r comma theta plus delta theta minus g r comma theta I plus g plus h r comma theta plus delta theta minus h r comma theta j. Now, if I try to calculate the area vector of a parallelogram, that is a vector and b vector, I have to calculate cross. So area vector is a cross b. A cross b is nothing but cross product of these two vectors that I have talked about, where cross product of these two vectors. What is the first vector? First vector, a vector, okay, a cross b is the area of the parallelogram. That is, a vector is g r plus delta r minus comma r minus g r comma theta I plus h r plus delta r comma theta minus r minus h r plus delta r comma theta j. Okay, this is a vector. It is same as g r plus delta r comma theta minus g r comma theta. This I can write as g r plus delta r comma theta, g r plus delta r comma theta minus g r comma theta divided by delta theta into delta theta. Okay, same as h r plus delta r comma theta minus r minus h r comma theta can be written as h r plus delta r comma theta minus h r comma theta divided by delta theta into delta theta. That is nothing but dx by d theta into delta theta plus di plus dy by d theta into delta theta j. Now a cross b is nothing but dx by d theta into delta theta I plus dy by d theta into delta theta j cross dx by d, I'm sorry, the horizontal side I have to divide by delta r because change is in delta r. So it is dx by dr into delta ri plus dy by dr into delta rj cross dx by d theta, that up one b vector, dx by d theta into delta theta I plus dx dy by d theta into delta theta j. If I do cross product, then it becomes dx by dr into dy by d theta minus dx by d theta into dy by dr, okay, and bracket close, delta theta delta r. So the area vector, now the actual computation is circular region, and then square root of a square minus x square minus y square dA dxy plane. This dA of xy plane converted into dx by dr into dy by d theta minus dx by d theta into dy by dr into delta theta delta r. That is for ij sub rectangle. Okay, if I go for full, I have to add every rectangle and it becomes now dx by dr into dy by d theta minus dx by d theta into dy by dy by dr and d theta dr or dr d theta. So full term, the dxy plane, dA plane is now converted into dx by dr into dy by d theta minus dx by d theta into dy by dr, okay, and then dr d theta. Same thing what we brought in, but approach is different. The dxy plane or d area plane we directly brought and replaced it by a vector cross b vector, a vector cross d vector, where a vector is dx by dr delta ri plus dy by dr into delta rj, whereas b vector is dx by d theta into delta theta I plus dy by d theta into delta theta j. If that is the case, cross product will lead. So this is the second proof. The third proof that we are going to talk now, if this is r theta plane, consider this is uv plane because we are going to talk parametric vector which is represented as r vector always. So if this is x, this is uv plane, and if this is uv plane, then this is xy plane. If this is uv plane, then this is xy plane. There is a rectangle in uv plane. This rectangle is mapped to some area in the xy plane. Now in xy plane, any point I can represent as p vector, where p vector is xi plus yj, or I can represent it as parametric vector, r vector. R vector of u comma v, where this is u plane, xy plane, x equal to function over u and v, x equal to guv, y equal to huv. If that is the case, then this position vector p will convert into parametric vector over u comma v. So this parametric vector u comma v. Now if I want to calculate area vector here, if this is a region on xy plane and with parametric vector r, then area is nothing but dr by du. If r is a vector of function u comma v, then dr by du, that is a vector along u direction. dr by dv is vector along this direction. So dr by du or area area vector is nothing but if area vector is represented by parametric vector r, parametric vector parametric vector r r u component cross r v component, dr by, if it is represented as, I mean, how I can represent the kind of how I can represent the area on the xy plane. Area on the xy plane would be r vector that is along x-axis and r vector along y-axis. If we do cross product, that will be area vector. The r vector along x-axis is dr by du, then multiplied by delta u. So any r vector I can represent as dr by du multiplied by delta u. I. Okay. dr by du multiplied by delta u. Okay, this is the kind of r vector cross product dr by dv multiplied by delta v. So area vector, if I talk about the area vector in xy plane, if I have a area rectangular area in UV plane, this rectangular area is mapped into some region in xy plane, where r is the kind of position vector. This is how it is available in the book. I am telling word by word. So if there is a corresponding area rectangular region in UV plane, it is mapped into the some surface area on XY plane, and then on the XY plane there are, if I consider that there are two vectors, one is along the x-axis direction, one is along y-axis direction. What I am trying to say that if I have a r vector, that is parametric vector, if I take any vector here, any position vector p on the xy plane, then p equal to xi plus yj. If I convert into the parametric vector, then it becomes p will become r vector, r on top of it one arrow, r vector in bracket u comma v. This is parametric vector for u and v. If that is the case, then dr by du, it is the derivative of r along the x-axis. Dr by dv, it is derivative along the j-axis. So dr by du, dr by du, dr r vector is nothing but dr by du into delta u, and r vector is nothing but dr by dv into delta v. If I want to calculate the kind of area vector, if I want to calculate the area vector, it will be dr by du, dr by du, dr by du into delta u, okay, dr by du delta u cross product dr by dv delta v. It is nothing but dr by du cross product dr by dv and outside multiplied by delta u delta v. So area vector for the, okay, I may not be very nice in explaining, but this is how it is in the book. I'll try to make my version of it. So the third proof is that through parametric vector, if I have a UV plane, there is a rectangle that is mapped into XY plane as some surface, and if I take if I take a kind of a vector, if I take a area vector is denoted by a position p. Okay, then p can be denoted as parametric vector of u comma v. Then the r vector, that is now p vector with a parametric u comma v, is denoted as r. So r on top of a vector sign u comma v. If that is the case, then r vector, that is the area vector, is nothing but dr by du into delta u. Okay, cross with dr by dv into delta v. So dr by du into delta u is r only. Cross dr by dv into delta v. If I do this cross, it becomes dr by du cross dr by dv and then dr du. Same thing. Now, if that is the case, then surface area in xy plane, that can be denoted in u and v as dr. So dr, whatever the r was earlier position vector xi plus yj. Now it got converted into parametric vector u comma v. If that is the case, then dr by du cross dr by dv dr du. So dx dy got replaced by dr by du cross dr by dv and dr du. Same thing what we are kept on talking, but this is not in terms of x and y. Just dr by du cross dr by dv and then dr du. Okay, now whatever we have done at the end result, it is same. So dr by du cross dr by dv is called Jacobian, or in our first term, that was dx by du dx by dui plus dx by duj cross product with dx by dvi plus dy by dvj is Jacobian. In second proof, in the second proof also, dx by du dx by dui plus dy by duj j cross with dx by dvi plus dy by dvj is the Jacobian. Here dr by du cross dr by dv is Jacobian. And right side anyway we have delta u delta v. So now anyone can compute it. What is the limit that we can take for the circular region? If I have a circular region that for which we are calculating minus a to a x is and y is minus a to a, then anyone can see the circular region r sine r x is r cos theta and y is r sine theta. So this is a polar coordinate system. In polar coordinate system, if there is a circle, then r would go 0 to a and theta would go 2 pi. So theta 0 to 2 pi and r is 0 to a, that is the radius. Now square root of a square minus r square. And what about dx by dr into dy by d theta minus dx by d theta into dy by dr? Dx by dr is cos theta. Dy by d theta is r cos theta. So r cos square theta minus dx by d theta dx by d theta, that is minus r cos minus r sine theta, and dy by dr sine theta minus minus plus. So r square cos square theta plus r square sine square theta. Okay. So I mean r cos square theta plus r sine square theta r. So net integration is now theta 0 to 2 pi r 0 to a square root of a square minus r square r dr d theta. Now it is simple to manipulate, then a square root of a square minus x square minus y square dx dy. Okay, this is two-dimensional Jacobian than that we talked about through three different proofs. Now we will same thing we will carry forward for three-dimensional proof, three-dimensional Jacobian. So we don't talk about dxy by d r theta. We will talk about dxyz by dr theta w. So that we will see in the next session. So this is how we will proceed.